The first step in automobile manufacturing is steel sheet stamping. The equipment used here is a 3,000-ton hydraulic press with pressure output capability of 3,000 tons, equivalent to 30,000 kilonewtons of force. The material being processed is cold-rolled steel sheet with thickness of 0.8 millimeters, material designation SPCC deep drawing grade steel. The steel sheet is first fed into the die positioning system. Positioning accuracy requirement reaches plus or minus 0.1 millimeters, achieved through cooperation of photoelectric sensors and mechanical positioning pins. After positioning completion, the upper die begins descending. Descent speed in initial phase is 20 centimeters per second. When approaching the steel sheet, speed reduces to 5 centimeters per second to ensure precise contact. At the moment of upper die contact with steel sheet, pressure begins gradually increasing. The stamping process employs cushion control technology. Pressure rise curve is precisely calculated, increasing from zero gradually to the set value of 2,500 tons. The entire pressurization process lasts 3.5 seconds. This duration is determined based on steel sheet thickness and material property characteristics. During maximum pressure holding phase, the upper die remains at lowest position for 1.2 seconds. This dwell time ensures steel sheet fully conforms to die surface, eliminating spring-back effect. Under tremendous pressure, steel sheet undergoes plastic deformation. Originally flat sheet material is pressed into three-dimensional car door panel shape, including all reinforcement ribs and mounting hole positions. After dwell completion, upper die begins rising. Rising speed matches descent, employing segmented control. Rapid rise phase is 20 centimeters per second. Final separation stage decelerates to 5 centimeters per second, avoiding workpiece deformation or die damage from excessive speed. The stamped door panel is removed from the die. At this point, material surface maintains excellent smoothness. Surface roughness is controlled within RA 1.6 micrometers. This provides ideal foundation for subsequent welding and coating processes. Total time for each stamping cycle is approximately 12 seconds. This press can produce 300 door panels per hour with extremely high efficiency. Die temperature also requires continuous monitoring. Through built-in cooling water channels, die temperature consistently maintains between 40 and 50 degrees Celsius. This temperature range ensures both processing quality and extends die service life. Die design life is 500,000 stamping cycles. Upon reaching this count, maintenance or replacement is required. Stamped body parts enter the welding workshop for assembly. The equipment used here consists of 6-axis industrial welding robots. Each robot is equipped with servo motor drive system with positioning accuracy reaching plus or minus 0.05 millimeters. The welding method employs resistance spot welding, the most commonly used joining process in automobile manufacturing. Welding electrodes are manufactured from copper-chromium alloy. Electrode tip diameter is 8 millimeters. Electrode cooling is achieved through internal water channels. Cooling water flow rate is 4 liters per minute with water temperature controlled between 15 and 20 degrees Celsius. Adequate cooling ensures electrode maintains stable performance in high-temperature working environment, extending service life. Welding parameters are precisely set according to sheet material thickness. For 0.8 mm thick steel sheet, welding current is set at 9,000 amperes. Welding time is 0.3 seconds. specifically 300 milliseconds. Electrode pressure is set at 3000 newtons. This pressure remains constant during welding process, ensuring tight contact between two steel sheet layers. The welding process divides into 3 stages. First stage is pre-compression. Electrodes apply pressure to workpiece before energizing, lasting 0.1 seconds. This stage expels air between sheet materials, ensuring good electrical contact. Second stage is electrical heating. Large current passes through electrodes and workpiece. Resistance heat generates at contact interface. Temperature rapidly rises above 1300 degrees Celsius. At this temperature, steel begins melting, forming nugget. Nugget diameter typically ranges 5 to 6 millimeters. This dimension is achieved through welding parameter control. Third stage is forging. After current cutoff, electrodes continue maintaining pressure for 0.2 seconds. During this stage, molten metal cools and solidifies under pressure, forming strong weld spot. Entire welding cycle requires only 0.6 seconds. One car body requires approximately 4,000 weld spots. Multiple robots work simultaneously, completing each weld spot sequentially according to predetermined program. Robot motion trajectory is optimized, pursuing shortest cycle time while ensuring quality. Welding process generates sparks and fumes. Sparks are formed from molten metal splatter with extremely high temperature exceeding 1500 degrees Celsius. Fumes are mixture of metal vapor and oxides. Workshop is equipped with powerful ventilation system. Air change rate reaches 15 times per hour, ensuring workplace air quality meets occupational health standards. Weld spot quality is detected through multiple methods. First is visual inspection. Qualified weld spots should have smooth surface without cracks or excessive splatter. Second is ultrasonic testing, capable of discovering internal incomplete fusion defects. For critical location weld spots, destructive testing is also required. Peel testing measures weld spot load-bearing capacity. Qualified weld spots should experience base material tearing rather than weld spot failure during peeling. Welded car bodies enter the grinding and polishing process. This stage aims to remove welding splatter, burrs and surface unevenness, preparing for subsequent coating. Grinding equipment includes pneumatic grinders and polishing machines. These tools are driven by compressed air with working pressure of 0.6 megapascals. Grinding process begins with coarse grinding. Aluminum oxide grinding wheel is used with grit size of 60 mesh. This coarser abrasive can rapidly remove larger unevenness. Grinding wheel diameter is 150 millimeters with rotation speed of 10,000 revolutions per minute. During operation, grinding wheel maintains 15 to 20 degree inclination angle with body surface. This angle ensures both cutting efficiency and avoids leaving deep scratches on surface. Coarse grinding stage primarily targets areas around weld spots. Approximately 50 square millimeters around each weld spot requires grinding. Operation employs reciprocating motion. Each movement distance is approximately 30 millimeters with overlap rate maintained at 30%. This working method ensures uniform surface treatment without missed or overground areas. Medium grinding stage uses 120 mesh grinding wheel. This stage aims to eliminate deeper scratches left by coarse grinding, further improving surface flatness. Rotation speed reduces to 8,000 revolutions per minute with correspondingly lighter pressure. After medium grinding, surface roughness reduces to approximately Ra 5 micrometers. Fine grinding stage uses 240 mesh grinding wheel. This is final grinding stage. Rotation speed further reduces to 6,000 revolutions per minute. Fine grinding focus is obtaining uniform consistent surface texture, providing ideal substrate for painting. After fine grinding, surface roughness reaches Ra 2 micrometers. Polishing stage uses wool polishing pad paired with polishing compound. Polishing compound contains extremely fine abrasive particles with particle diameter between 1 and 3 micrometers. Polishing pad rotation speed is 3,000 revolutions per minute. This lower speed avoids generating excessive heat. During polishing, compound softens under frictional heat. Abrasive particles perform microfine cutting on surface. Polishing process employs circular motion. Polishing pad moves smoothly along curved surface, ensuring every area receives uniform treatment. Polished surface achieves mirror effect with roughness reduced below Ra 0.5 micrometers. This surface quality ensures subsequent primer can adhere properly. Final paint surface can present perfect gloss. Entire grinding and polishing process generates substantial dust. Workshop is equipped with dust collection system. Dust is collected through suction pipelines to centralized treatment device. Workers wear dust masks and goggles ensuring health and safety. Lighting employs shadowless lamps with illumination intensity reaching 1000 lux, allowing operators to clearly see every surface detail. After face coat spraying, body immediately enters final drying room. This time baking temperature is 140 degrees Celsius with duration of 40 minutes. High temperature promotes complete coating curing while also heat treating entire car body, eliminating internal stress. After drying completion, total paint film thickness reaches 135 micrometers with dry film thickness approximately 95 micrometers. Entire painting process requires strict quality control. Each batch undergoes paint film thickness measurement using electromagnetic induction thickness gauge, testing at 20 standard positions on car body. Gloss measurement is also performed using 60-degree angle gloss meter. Qualified paint surface gloss should range between 85 and 95. Additionally, visual inspection checks surface for sagging, orange peel, color difference and other defects. While car body is being painted, powertrain is assembled on another production line. Engine is heart of automobile. Its assembly process requires extremely high precision. Engine being assembled here is inline 4-cylinder turbocharged engine with displacement of 2 liters and maximum power of 180 kilowatts. Assembly begins with cylinder block. Cylinder block is cast from aluminum alloy, weighing 35 kilograms. Before assembly, cylinder block requires precision machining. Cylinder bore roundness error does not exceed 0.01 millimeters. Surface roughness Ra value is 0.4 micrometers. This precision ensures piston can move smoothly within cylinder while maintaining good sealing. Cylinder head installation is critical step. Cylinder head is also made from aluminum alloy, covered with cooling water passages, oil passages and air passages. Before installation, cylinder head gasket is placed between cylinder block and cylinder head. Cylinder head gasket is made from multi-layer stainless steel and graphite composite material with thickness of 1.5 millimeters. This seemingly simple gasket must withstand pressure up to 100 atmospheres and temperature of 2000 degrees in combustion chamber. Cylinder head is secured by 10M10 bolts. These bolts are manufactured from high-strength alloy steel, grade 12.9, with tensile strength reaching 1,200 megapascals. Bolt tightening employs three-stage torque method. First stage pre-tightens to 40 Newton meters, second stage increases to 80 Newton meters, third stage rotates additional 90 degrees. This torque plus angle method ensures each bolt obtains uniform and accurate preload. Crankshaft installation requires extreme care. Crankshaft is one of most precision components in engine, manufactured from high-strength forged steel, weighing 28 kilograms. Crankshaft main journal diameter is 60 millimeters with precision requirement of 0.005 millimeters. During installation, thin layer of assembly oil is first applied to journal, then crankshaft is gently placed into cylinder block main bearing seats. Main bearing caps are installed using hydraulic tightening tools. Each bearing cap uses two M12 bolts with torque setting of 120 Newton meters, error not exceeding plus or minus 2%. After tightening, feeler gauge checks axial clearance. Standard value is 0.1 to 0.25 millimeters. If clearance is excessive or insufficient, thrust washers of different thickness must be replaced for adjustment. Piston and connecting rod assemblies are pre-assembled at dedicated workstation. Piston is cast from aluminum silicon alloy. Top has complex combustion chamber shape for optimizing combustion efficiency. Piston has 3 rings. Topmost is compression ring for sealing. Middle is second compression ring for auxiliary sealing. Bottommost is oil ring for scraping excess oil. End gap of each piston ring requires precise measurement. Standard value is 0.3 to 0.5 millimeters. Piston connects to connecting rod small end through piston pin. Piston pin has hollow structure with diameter of 25 millimeters and wall thickness of 4 millimeters. This structure reduces weight while ensuring strength. Piston pin is secured by circlip preventing axial movement. Connecting rod big end connects to crankshaft using separable bearing shells. Bearing shell inner surface is plated with Babbitt alloy layer of 0.3 millimeters thickness. This material possesses excellent anti-friction and wear-resistant properties. Camshaft controls intake and exhaust valve opening and closing. This engine employs dual overhead camshaft design. One controls intake valves, other controls exhaust valves. Camshaft is manufactured from forged steel. Cam sections undergo high-frequency quenching treatment with hardness reaching HRC 58 to 62. Cam lift precision requirement is plus or minus 0.05 millimeters. This directly affects engine power output and fuel economy. Timing system ensures camshaft maintains precise phase relationship with crankshaft. Timing chain drive is used here. Chain is roller type with pitch of 9.5 millimeters. Chain maintains appropriate tension through hydraulic tensioner with tension force of 500 newtons. Timing adjustment precision requirement is plus or minus 1 degree crankshaft angle. This equals 0.003 seconds time precision. Turbocharger is installed on exhaust side. Turbocharger uses exhaust energy to drive compressor, increasing intake pressure to 1.5 atmospheres. Turbine impeller speed can reach 200,000 revolutions per minute. Impeller tip linear velocity approaches speed of sound. Such high speed requires impeller undergo precise dynamic balancing. Unbalance amount must not exceed 0.5 gram millimeters. After engine assembly completion, cold break-in is performed on test bench. Test bench simulates engine working state on automobile. Electric motor drives engine crankshaft rotation. Speed gradually increases from 1,000 revolutions per minute to 3,000, running continuously for 2 hours. During break-in process, oil pressure, water temperature, vibration and other parameters are monitored, ensuring all indicators remain within normal range. When both car body and powertrain are ready, chassis and tire assembly begins. Tires are only contact point between automobile and ground. Installation quality directly affects driving safety and comfort. Tires being installed here are 225 mm wide 45 aspect ratio, 18-inch radial tires. Tire installation begins with wheel hub. Wheel hub is manufactured from forged aluminum alloy with 5-spoke design, weighing 12 kilograms. Before installation, wheel hub requires runout inspection. Both radial runout and axial runout must not exceed 0.5 millimeters. During inspection, wheel hub is mounted on dedicated inspection bench. Wheel hub is rotated while dial indicator measures runout values at various positions. Tire and wheel hub combination uses automatic tire mounting machine. First, wheel hub is secured on mounting machine's center positioning shaft. Then tire is laid flat. Mounting machine's pressure head descends, pressing one side's tire bead into wheel hub's rim well. This process requires approximately 2 tons pressure with entire action lasting 3 seconds. After first side bead installation, mounting machine rotates tire 180 degrees, pressing in other side's bead. After both side beads are installed, inflation is required. Initial inflation uses high pressure air with pressure reaching 0.5 megapascals. High pressure airflow rapidly pushes bead toward rim edge, producing crisp pop sound indicating bead correct seating. This process is called bead seating. After bead seating, air pressure is adjusted to standard value. Front tire pressure is 250 kilopascals. Rear tire pressure is 240 kilopascals. Tire pressure measurement uses digital tire pressure gauge with precision of 1 kilopascal. Correct tire pressure has important impact on both tire life and fuel economy. Excessive pressure causes accelerated center wear. Insufficient pressure increases rolling resistance and fuel consumption. Tire assembly requires dynamic balance testing. Tire assembly is mounted on balancing machine. Balancing machine rotates tire at 300 revolutions per minute. Built-in sensors detect imbalance amount. If imbalance exceeds 10 grams, balance weights must be attached to wheel hub edge. Balance weights come in 5 gram, 10 gram, 15 gram and other specifications. Operator selects appropriate weight based on position and weight displayed by balancing machine. After balancing completion, tire assembly is installed on vehicle. Installation uses pneumatic wrench. First, 5M14 wheel hub bolts are hand-threaded. Then pneumatic wrench tightens in diagonal sequence over 3 stages. First stage pre-tightens to 50 Newton meters, second to 80 Newton meters, third reaches final torque of 110 Newton meters. Stage tightening ensures wheel hub and flange surface tight contact, avoiding deformation from single large torque application. After tire installation, torque wrench performs reinspection. Torque wrench is mechanical type, producing click sound when reaching set torque. During reinspection, each bolt is checked sequentially, ensuring torque reaches standard value. This step increases workload but is necessary for safety assurance. Loose bolts could cause wheel detachment with unimaginable consequences. Finally, air tightness inspection is performed. Tire is immersed in water tank, observing whether bubbles emerge. If leakage is discovered, valve stem and wheel hub tire junction require reinspection. Valve stem employs rubber material with internal one-way valve structure, allowing air entry but preventing escape. Valve stem service life matches tire. When replacing tire, valve stem should also be replaced simultaneously. After vehicle external assembly completion, interior fitting stage begins. Interior affects not only riding comfort but is also an important manifestation of automobile class and quality. Interior assembly requires meticulous manual operations, forming sharp contrast with previous mechanized production. Dashboard installation is first step of interior assembly. Dashboard is complex component integrating display screen, air conditioning vents, audio system, airbag and other functional parts. Dashboard body is ABS plastic injection molded with surface covered by soft polyurethane foam layer of 5 mm thickness. This soft layer provides good tactile feel while providing cushioning effect during collision. During installation, 2 workers deliver dashboard into vehicle from both door sides. Dashboard connects to car body through 6 fixing points. Each fixing point uses M8 bolt with torque of 25 Nm. Before installation, various wire harnesses must be connected first, including power harness, signal harness, lighting harness and others. Each connector has foolproof design, only insertable in correct direction, avoiding misconnection. After dashboard installation completion, functional testing is performed. Ignition switch is turned on, checking whether instrument panel indicator lights illuminate normally. Air conditioning system is tested, confirming vent air volume is normal and temperature control is accurate. Audio system is tested, checking all speakers work normally. These tests use dedicated diagnostic instruments capable of rapidly identifying any abnormalities. Seat installation equally requires precise operation. This car is equipped with power-adjustable seats. Seat frame is welded from high-strength steel tubes. Seat cushion and backrest are filled with high-density polyurethane foam with density of 50 kg per cubic meter. Foam surface is covered with leather upholstery. Leather thickness is 1.2 mm, specially treated with anti-stain and anti-UV properties. Power seat is equipped with 4 adjustment motors, separately controlling seat fore-aft position, seat height, backrest angle and lumbar support. Each motor rated power is 30 watts, driving adjustment mechanism through worm gear mechanism. Adjustment speed is 5 mm per second. This speed neither feels too slow nor difficult to position precisely from excessive speed. Seat is secured on floor slide rail through 4 M10 bolts. Bolt torque is 50 Nm. This torque ensures seat will not detach from fixation during collision. Slide rail employs cold-rolled steel plate stamping with surface galvanized treatment preventing rust. Slide rail interior has precision steel balls ensuring smooth seat adjustment without binding. Door trim panel installation is relatively simple but requires care. Trim panel is polypropylene injection molded, secured by 10 plastic clips and 4 screws. Clip design is ingenious. Insertion requires certain force but removal only needs gentle prying with dedicated tool. This design facilitates trim panel removal during maintenance while ensuring no loosening during normal use. Trim panel integrates multiple functional components including window lift switch, mirror adjustment switch, door lock switch and others. These switches' tactile feel is carefully calibrated. Button force is 2 to 3 newtons. This force provides clear feel without effort. Switch life is designed for 100,000 operations, far exceeding actual operation count during vehicle normal use period. Carpet installation seems simple but actually has particulars. Automobile carpet is knit formed from polypropylene fiber material with waterproof rubber layer coated on back. Carpet connects to car body floor through multiple Velcro fixing points. This fixing method prevents carpet displacement during use while facilitating removal for washing. Safety belt installation is most critical element in interior assembly. Safety belt anchor points must be secured in car body high-strength areas capable of withstanding 20 kN tensile force. Safety belt retractor interior has complex mechanical structure. Under normal conditions, belt can be freely pulled out. During emergency braking or collision, retractor instantly locks preventing occupant forward motion. Headliner installation is final step of interior assembly. Headliner is manufactured from fiberglass and headliner installation is final step of interior assembly. Headliner is manufactured from fiberglass and polyurethane composite material with surface covered by knitted fabric. Headliner is secured through peripheral clips and several central screws. Installation requires two-person cooperation. One person inside vehicle supports headliner while other person from outside sequentially secures connection points. After headliner installation completion, entire vehicle interior presents complete unified effect. After vehicle external assembly completion, interior fitting stage begins. Interior affects not only riding comfort but is also important manifestation of automobile class and quality. Interior assembly requires meticulous manual operations, forming sharp contrast with previous mechanized production. Dashboard installation is first step of interior assembly. Dashboard is complex component integrating display screen, air conditioning vents, audio system, airbag and other functional parts. Dashboard body is ABS plastic injection molded with surface covered by soft polyurethane foam layer of 5 mm thickness. This soft layer provides good tactile feel while providing cushioning effect during collision. During installation, two workers deliver dashboard into vehicle from both door sides. Dashboard connects to car body through 6 fixing points. Each fixing point uses M8 bolt with torque of 25 Nm. Before installation, various wire harnesses must be connected first, including power harness, signal harness, lighting harness and others. Each connector has foolproof design, only insertable in correct direction, avoiding misconnection. After dashboard installation completion, functional testing is performed. Ignition switch is turned on, checking whether instrument panel indicator lights illuminate normally. Air conditioning system is tested, confirming vent air volume is normal and temperature control is accurate. Audio system is tested, checking all speakers work normally. These tests use dedicated diagnostic instruments capable of rapidly identifying any abnormalities. Seat installation equally requires precise operation. This car is equipped with power adjustable seats. Seat frame is welded from high-strength steel tubes. Seat cushion and backrest are filled with high-density polyurethane foam with density of 50 kg per cubic meter. Foam surface is covered with leather upholstery. Leather thickness is 1.2 mm, specially treated with anti-stain and anti-UV properties. Power seat is equipped with 4 adjustment motors, separately controlling seat fore-aft position, seat height, backrest angle and lumbar support. Each motor rated power is 30 watts. Driving adjustment mechanism through worm gear mechanism. Adjustment speed is 5 mm per second. This speed neither feels too slow nor difficult to position precisely from excessive speed. Seat is secured on floor slide rail through 4 M10 bolts. Bolt torque is 50 Nm. This torque ensures seat will not detach from fixation during collision. Slide rail employs cold-rolled steel plate stamping with surface galvanized treatment preventing rust. Slide rail interior has precision steel balls ensuring smooth seat adjustment without binding. Door trim panel installation is relatively simple but requires care. Trim panel is polypropylene injection molded, secured by 10 plastic clips and 4 screws. Clip design is ingenious. Insertion requires certain force but removal only needs gentle prying with dedicated tool. This design facilitates trim panel removal during maintenance while ensuring no loosening during normal use. Trim panel integrates multiple functional components including window lift switch, mirror adjustment switch, door lock switch and others. These switches' tactile feel is carefully calibrated. Button force is 2 to 3 newtons. This force provides clear feel without effort. Switch life is designed for 100,000 operations, far exceeding actual operation count during vehicle normal use period. Carpet installation seems simple but actually has particulars. Automobile carpet is knit formed from polypropylene fiber material with waterproof rubber layer coated on back. Carpet connects to car body floor through multiple Velcro fixing points. This fixing method prevents carpet displacement during use while facilitating removal for washing. Safety belt installation is most critical element in interior assembly. Safety belt anchor points must be secured in car body high-strength areas capable of withstanding 20 kilonewtons tensile force. Safety belt retractor interior has complex mechanical structure. Under normal conditions, belt can be freely pulled out. During emergency braking or collision, retractor instantly locks, preventing occupant forward motion. Headliner installation is final step of interior assembly. Headliner is manufactured from fiberglass and headliner installation is final step of interior assembly. Headliner is manufactured from fiberglass and polyurethane composite material with surface covered by knitted fabric. Headliner is secured through peripheral clips and several central screws. Installation requires two-person cooperation. One person inside vehicle supports headliner while other person from outside sequentially secures connection points. After headliner installation completion, entire vehicle interior presents complete unified effect. After electronic system testing qualification, vehicle enters final quality inspection stage. This is last checkpoint before vehicle rolls offline. Inspection content covers appearance, function, safety and all aspects. Quality inspection is performed by dedicated QC team using detailed inspection checklist, verifying item by item. Appearance inspection begins with car body paint surface. Inspector carefully observes paint surface under bright inspection lamp with illumination intensity reaching 2000 lux. Inspection lamp uses daylight color temperature approximately 6000 Kelvin. This light source most truthfully reproduces color. Inspector observes from different angles, searching for possible defects including scratches, dents, color differences, orange peel, sagging and others. 4 discovered defects, classification into 3 categories based on severity. Class A defects are serious defects such as obvious dents or large area color differences requiring rework. Class B defects are general defects such as small scratches or slight orange peel with rework decided case by case. Class C defects are minor defects such as extremely small dust spots, acceptable. Number of Class C defects allowed per vehicle does not exceed 5. Car body gap measurement uses dedicated gap gauge. Gap gauge is set of metal feelers of different thickness from 0.5 mm to 5 mm. Inspector inserts gap gauge into gaps between doors, hood, trunk lid and car body, measuring gap width. Standard requires gaps between 3 and 5 mm with gap difference at left-right symmetric positions not exceeding 0.5 mm. Wheel alignment parameter detection is performed on dedicated 4-wheel aligner. Vehicle drives onto aligner with turntable and slip plate below each of 4 wheels. After turntable and slip plate release, wheels can freely rotate and move fore aft, eliminating tire ground friction influence. Aligner uses laser or camera to measure wheel toe angle, camber angle and caster angle. Front wheel toe angle standard value is 0.1 to 0.3 degrees. This tiny angle makes two front wheels slightly incline inward. Toe angle function compensates for tire rolling characteristics, maintaining stability during straight driving. Camber angle standard value is -0.5 to -1 degree. Negative value indicates wheel top inclines inward. This camber improves cornering stability. Rear wheel alignment parameters are similar to front wheels but with smaller adjustment range. Some vehicle models have fixed rear wheel alignment parameters without adjustment capability. This design simplifies suspension structure, reducing cost. During inspection, if alignment parameters exceed standard range, suspension components require adjustment until parameters qualify. Braking performance testing is conducted on dedicated roller dynamometer. Test bench has 4 roller groups corresponding to 4 wheels. Vehicle drives onto test bench with 4 wheels placed on rollers respectively. Rollers begin rotating, driving wheel rotation with speed gradually increasing to 40 km/h. Then test personnel depress brake pedal, measuring braking force of each wheel. Front wheel braking force should reach above 30% of vehicle weight. Rear wheel braking force should reach above 20% of vehicle weight. More importantly, braking force of 4 wheels must be balanced. Braking force difference between left and right wheels does not exceed 10%. If braking force is unbalanced, vehicle will pull to one side during emergency braking, presenting safety hazard. Lighting detection uses automatic lighting tester. Vehicle stops 5 meters in front of tester. Tester's photoelectric sensors align with vehicle headlights. Low beam is turned on. Tester measures light projection direction and brightness. Low beam optical axis should incline downward 1 degree, deviate rightward 0.5 degrees. This projection angle illuminates forward road surface without dazzling oncoming driver. Low beam brightness should reach above 12,000 candela. High beam testing method is similar but with higher requirements. High beam optical axis should be horizontal forward with brightness reaching above 50,000 candela. Turn signal flashing frequency test requires between 60 and 120 times per minute. This frequency attracts attention without causing annoyance. Vehicle noise testing is performed in semi-anechoic chamber. Semi-anechoic chamber walls and ceiling are covered with sound-absorbing material with background noise below 30 decibels. Vehicle idles inside chamber. Noise level is measured at driver's seat position. Qualification standard is idle noise not exceeding 40 decibels. Then engine speed is raised to 3,000 revolutions per minute, measuring acceleration noise with requirement not exceeding 75 decibels. Interior air quality detection is newly added item in recent years. New car interior materials release formaldehyde, benzene, toluene and other volatile organic compounds. During detection, vehicle is sealed with air conditioning off, standing for 2 hours. Then air sampling pump extracts interior air for analysis of various harmful substance concentrations through gas chromatography. Formaldehyde concentration requirement is below 0.1 milligrams per cubic meter. Benzene concentration below 0.11 milligrams per cubic meter. After all inspection items completion, inspector signs inspection report. Report records detection data and judgment results for each item. Qualified vehicles receive qualification certificate label on windshield, preparing to enter final roll-off procedure. Unqualified vehicles return to corresponding workstation for rectification. After rectification, comprehensive reinspection is required. After confirmation of qualification through all inspection procedures, vehicle finally arrives at roll-off moment. This is final stage of automobile manufacturing process, marking transformation from parts to complete product. Although industrialized production, this moment remains worthy of celebration. Vehicle slowly exits inspection area, entering roll-off passage. Roll-off passage, both sides are installed with bright LED light strips, illuminating entire space. Floor is laid with anti-slip rubber matting ensuring vehicle safe passage. Passage width is 4 meters, sufficient for accommodating vehicle and workers on both sides. At roll-off passage endpoint, final inspection station is set. This is final brief inspection confirming vehicle overall condition. Inspector walks circle around vehicle, checking whether 4 wheels are all normally inflated, whether doors open and close smoothly, whether lights work normally. This inspection requires only 2 to 3 minutes but is indispensable. After final inspection completion, vehicle drives onto electronic weighbridge. Weighbridge precision is 10 kilograms, accurately measuring vehicle curb weight. This car's standard curb weight is 1,580 kilograms. Actual measured value is 1,575 kilograms with error within allowable range. Weight data is recorded in vehicle file as important technical parameter. After weighing, vehicle continues forward, passing through automatic license plate recognition system. System camera photographs vehicle VIN code, vehicle identification number. VIN code consists of 17 characters containing manufacturer, model, production year, production plant and other information. System automatically associates VIN code with order information, confirming this vehicle's destination and customer information. Roll-off passage exit is gentle slope. Vehicle drives down slope exiting production workshop. Slope gradient is 5%, specifically descending 1 meter for every 20 meters forward. This gradient is gentle. Vehicle descends smoothly at 10 kilometers per hour speed. Sunlight shines through workshop door, illuminating vehicle's glossy paint surface. After vehicle exits workshop, it enters finished vehicle storage area. Storage area is massive parking lot capable of simultaneously parking thousands of automobiles. Ground is painted with neat parking lines. Each parking space has numbering.
gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Exit shift like clouds in the dark. A symphony of cogs finding their spark. Atmosphere fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still serene. A gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Tessers shift like clouds in the dark. A symphony of cogs finding their spark.